Okay, the second speaker is Matthew Flatt. He's going to talk about lightweight semantics engineering with Redex. Please give him big hands.
So a lot of what I'm talking about today is Robbie's work most directly. Collaborating also with Matthias, building directly on a lot of his ideas. Redex is an executable semantics, I would say, at the research paper level of abstraction. Thanks to Xiaohong for giving us a great setup. He's put your head in the right space. We're doing very much the same sorts of things here. We are writing some program in Racket using the Redex domain-specific language. You write down a grammar, reduction rules, judgment forms. Maybe what you get out is, you can run those reduction rules as an interpreter. You can generate some tests to make sure it means what you think it means, typeset your rules for a paper, and so on. Just to get us started a little bit on the comparisons, things I can compare most easily that I know. K, which you've had a great introduction to, and very similar sort of ideas and foundation here. We're going to write a grammar, we're going to write reduction rules. K, if you're building something big, like real-world programming systems, you want K, not Redex. Right? So Redex is going to be this lightweight prototyping, writing a paper, exploring some part of a language. And what I hope to do today is give you a sense of how that feels. So we'll try to work through some code on that. Another thing you may think of in comparison is OT, because we're going to emphasize using other backends like to typeset or maybe prove things. But OT is not so embedded, and Redex gives you more of an escape. You can get out to Racket and do whatever you need to do and get back in the world. That means you have more of an obligation to set up some bridges, right? The thing about OT is you're in this declarative language, and then it can do a lot for you. It can prove things directly in typeset. And you may have to do more plugins in exchange for the flexibility in Redex. And you'll get a sense of what I mean as we go through the example. I'm not going to focus on these things, but there are some extensions to Redex to get you into the proof world. But most of what I'm going to show you today is just about running the interpreter and testing it and exploring it in that way. All right, so know that there are further things that you can do with Redex as an input, but I'm going to focus really just on the interpreter part and running it and seeing what it looks like. Okay. Redex is used for some papers, and I just did a sort of naive search and found a few recent papers that use it. So you may have seen it in use before, but I want you to be on the producer side today to see what it looks like to actually run the language and use it. So let's jump right into that. Here is a grammar starting at a similar point that Xiaohong started us starting in K. So I'm going to take this code, not my mail, but go over to Dr. Racket. And you see I've got require Redex there after #lang Racket. I'm going to paste this in. When I run this, okay, nothing happens, right? We've just defined the grammar. So this is the grammar has this identifier LC because we're going to write down terms, but the terms are not inherently attached to this grammar. Anything we want to do, like reduction rules, will say with respect to LC, with respect to this grammar. So we're defining some non-terminals here, obviously, E for expression, X for variables, and I'm just going to throw in some integers because it makes examples easier to write down. You will recognize this as the lambda calculus, and so I didn't need to tell you what LC was. I'm going to have multiple variables just so I can use some dots. So lambdas take any number of arguments, and so function calls have any number of argument expressions there. Variable not otherwise mentioned. This giant name is a built-in name. It says that if I have not used a letter anywhere else, I mean that to be a valid variable name. Not a letter, but any identifier, right? So I shouldn't use E as an identifier, but I can use double E or emphasis or something like that, right? So now that I've got this grammar, we could do more things, but the first thing I can do is just do a Redex match to say, like, with respect to LC and the pattern E. So I'm asking, is this, in fact, a term? 0. Right, so the term form is really quote, except it's sensitive meta functions, which we'll get to. So I'm just writing the term 0 and say, is that an expression according to my grammar? And what should the answer be? That should be true, right? What if I say lambda 0. Is that a term? That looks badly formed, right? So we should expect a false. And what if I say lambda x0 instead? Right? We're back in a good term world. Lambda xy is fine. But I can't put two expressions there with no parentheses, right? That's no good. But I could apply 0 to 8. Now, of course, applying 0 to 8 is not going to make any sense if you call this function. But that's not the grammar's problem, right? The grammar is just saying grammatically that's well formed. Right? I might want to talk about errors in this language. So Redex match is another built-in thing that you write some pattern here. I could also ask, is this two expressions next to each other? I've written this wrong, but suppose I try this. It's not, right? It's one big expression. So it should say false. What if I say 1, 2? That looks like two expressions sitting next to each other in parentheses. It's still going to say false, though. What if I make it 1, 1? Oh, now it says true. What's happening is E with no subscript is the E for this pattern. And so it's making sure it's the same E. That's sort of unclear. I might have been better off writing _1 in both of these places. So underscores are special. That says an instance of E, a particular instance of E. Right? Or if I put E1, E2 now I can write 13 or some other name here, and now it's true. All right? So that's an introduction to the idea of patterns. And we can use dots like, do I have any number of expressions here? And now I can write 3 of them, and so on. Everyone with me? Stop anytime you have a question, of course. Let me throw in some of the other examples here. Yes?
So do you have to use the letter E?
I do have to use the letter E if I'm talking about expressions. Yes. Yeah, so the question. Yeah.
So do you have to use the letter E like whenever you want to match Redux the terms?
Exactly. It's important that I use the letter E. You can see the binding arrow now that I've moused over it to say that's talking about an expression, a particular expression. Yeah. They don't have to be single letters. I've just chosen single letters for compactness here. I'll throw out some other examples. I think we've tried all of these kinds of things though, right? So here I've got an application of a function of 2 arguments to 2 arguments. So all those should be true. Yeah. And of course, if I wanted to write some tests to make sure that things are working, I might require rack unit, say, and just use a check true. Right? And if I get this wrong somehow, if I said those need to be the same term and it fails, then I get an error. So this is another example of the embedded nature. You just use the usual racket stuff like the rack unit to write test suites. All right, let me correct this so it doesn't complain as we go forward. Okay, so that was just my grammar, but I want to start writing some reduction rules. I'm going to do this in the usual way, which means I really need to distinguish between expressions that are not yet values and values. And the way we do that in a paper often is we say expressions can be things like variables and function calls, but they can also be values, which is where lambdas sit, as well as numbers. So I'm going to refine my grammar this way. Put this in place, and well, I haven't really changed anything. I've just given myself an extra name here. So all the things work as before. And now that I have that, then I can write the reduction rule that says call by value lambda calculus. When you have a function call, you need to have values for the arguments, and then you can substitute them in. Okay, this gets a bit more complicated, so let me copy this over and explain the pieces. Okay, so we've got just a regular racket defined of arrow v, but arrow v is going to stand for a reduction relation. So reduction relation is a built-in thing that's with respect to that grammar. It says the domain is E, so this is a reduction relation that works on expressions. Redex has no idea I meant expression by E, but this is what tells it with respect to this reduction relation. Codomain is the same by default. And then here's the rule. We're saying rewrite lambda x with body E applied to arguments v into, well, substitute x with v in E. Where does subs come from? We'll come back to that. You see this somewhat unusual ... underscore arg. That means make sure there's the same number of arguments, actual arguments as formal arguments, formal parameters, right? So underscore, you can use underscore with dots. By default, dots mean separate things, unlike variable names, or unlike non-terminal names. But you can make them explicitly the same by using an underscore. And so if we apply this reduction relation, this looks like this lambda applied to 2 and 3. We should get a 2 out, right? Let's try it. We did not get a 2 out. Now we got an extra set of parens because apply reduction relation tells you all the possible results here. What we got is subst x, etc., right? Why didn't it substitute? Well, what is substitution? Nobody said, right? So this is sort of the lightweight, flexible nature of Redex. If you didn't define something, it assumes it's a literal. And then there was no more reductions to do, and so that's what you got, right? Right? What if we wanted to define substitution? Surely we do. Here's one way to do it. Here I'm just doing it the hard way, just writing it out all myself. You could read this. I'll just highlight a few things maybe. This says when we substitute x with the same x going to v, then we should get v out. If x and it's any other thing, then we just leave it alone, right? Now, meta functions as a convenience go top to bottom. So this second one won't match. If it's the same x, I could be more explicit and write some side condition that says they have to be different, then the order doesn't matter. And so on, right? So this is saying I've got some x zeros followed by an x and some more x twos, and it's the same x. Well, then it's shadowing. I shouldn't change anything. But in this case, I've got some different x, and so I should substitute recur into the body. Yep?
Is the second rule redundant? Like if you don't write it, the subst x prime, or if you don't write it?
If I leave this one out, then Redex will complain. I don't know what subst to do. It won't just leave it as subst. It will complain at that point, because I have said subst is a meta function. Yeah. Yeah, define meta function is the thing here that's defining subst with respect to the language LC. Yep?
One thing that is sometimes annoying when doing something like this in a system like Rock is that you have like the same thing as an expression and as a value, and you need to convert between them. I don't see anything here dealing with that. Do you get this for free somehow?
You get this for free. So if I say, does Redex match? I can type LC is 1 an expression? Yes. Is it a value? Yes. They're just non-terminals. I'm just matching them, right? V is included in E. So yeah, I don't have to, in this case, worry about the coercion.
So it's like one big grammar, basically, and the non-terminals just carve out different pieces of it.
Exactly. So in other words, a term is not attached to a non-terminal. It's not even attached to a language. I could have LC prime that has other interpretations, and I could use the same term with both of them.
Okay, thanks.
Again, that's part of the lightweight sort of dynamic programming sort of flavor here. Great question. Okay, so now I have defined subst. I guess I meant to hit run here. And now we do reduce to 2. Right? Make sense? Okay. That's one step. What if we had more things in here? Like what if I had lambda z, x, and let's pass the y in. What's going to happen here? Are we going to get 2 or is it going to stop? And the answer is going to stop. Apply reduction relation applies the reduction relation just once. If you want to keep going, well, use apply reduction relation star. Which is keep going. And now it'll find me all the ways it could keep going. And I seem to have not kept going the way I expected. Why is that? I actually don't know. All right, well, we'll figure this out. Just to make sure we can look at traces, like.
Does it have to be Unicode lambda?
Oh yes, thank you. Yeah, it wasn't actually a lambda. For some reason, I thought it would be a good idea to make myself convert it to Unicode every time. Great catch, right? So I was going to see in the traces that it got stuck. So this is demoing another tool. But here you can see the traces go through. Thank you. All right. And there was nothing like, because lambda was not otherwise mentioned, it counted as a variable name and so on. It was still a well-formed term. All right. We all know the trade-offs of a flexible dynamic language. It may have felt a little dumb that I wrote out substitution myself. Of course, it's so common there is built-in support for that. Let's switch over to it. So binding forms goes in the grammar here. And then I can use substitute instead of sub. So substitute is the built-in thing. The that takes advantage of these binding forms. So this just says, when you have this kind of thing, which happens to fit in the grammar of term, then these X's are available in E, and so on. There's a little sublanguage for binding. And so now I can use substitute. I don't need subst anymore. And we'll still get the same things that we got before, I hope.
You had a double T.
I had a double T, so substitute misspells. You guys are great at this. All right, and so you see we did get the same result. Let me try to show you just a couple of more things. Typesetting, because this is for papers, we want to typeset things. So language depict takes says typeset the grammar with non-terminal Z and V for me. And the other one's going to typeset a reduction rule. You can see it's kind of small there, right? The default fonts are set up. But we are in just Racket, and these are generating pictures. So let's just use the pict library, and now we have the scale function, so we can make it twice as big. And now you can see. Okay. Or,
LaTeX?
Well, we usually generate PDF and then drop the PDFs into LaTeX, and it has the right bounding box, so it even works in line in the text. Right, as you may expect. There are various parameters to control the style of this thing, so that illustrates one of them. One thing you see is it's a bit dissatisfying that substitute is spelled out here as a meta function. That's the default typesetting of a meta function. So sometimes you want to take more control, and so here is a big pile of code. Typesetting is often like most of the code when you get ready to make the paper. Because you want to tweak this, you don't want to say substitute, you want to use the standard shapes there, so I need to scale it again, but the exact details of this are not all that important, but I fixed up the dots and I fixed up substitution, so it looks on this last line the way you would expect it to look. Right. All right, so we have this whole picture library, so you have lots of flexibility in how you put things together. I think I'm running out of time, so apply reduction relation star, I showed you already. If I do more examples, then we'll discover that it doesn't know how to evaluate sub-expressions. And why would it? Because I've just said, my reduction rule here says, take exactly this shape and match it, and it doesn't say this can appear somewhere down inside. Okay. So the way we do that in reduction semantics, Matthias style is with context. And so here I'm defining another thing that I would add to my grammar. I think I have time to do just this one more thing. So I'm going to add C here, and this is whole is a built-in thing to cooperate with in whole, as we'll use in the revised reduction rule. So it says a context is either a whole, or you got some number of values in a context and then some number of expressions. And so now we have this revised rule that I will drop in place of the old one. All right, so now my old examples still work. Let's turn off the typesetting. All right, I'm still so apply reduction relation star will still give us 2, and now I can nest these, right? So I could have, let's move the application out. You know how this works. I probably don't need to go all the way through it, but here we go. We should get 10 out this time, right? No, 2, because it's throwing away the 10 and giving us a 2. All right, so you do that. Now, if you've done any of this context stuff, it's easy to mess this up and put an E here instead, right? If I do this, I still get 2 out, but that's because it's confluent. So if I use traces, oh no, it's not, I don't have any ambiguity. If I get another example, there could be multiple ways of doing things. So in this one here, the second term, it turns out there are multiple ways to do it. And if I use traces, then it will show you the different paths through. Let's do that second one. So now we get, instead of just a linear list of boxes, we get a graph, and it can show you. And then you may look at this, you may run traces and say, that's not what I meant. I meant for it to always be a deterministic step. We have an example in this case, but maybe you wanted to make sure of that, so you can write a unique step property. like this. And then you can use Redex check, which is like quick check for Redex, and it'll go find you terms. It'll go find a term. In this case, it'll find it right away. Find a term that is not a unique step. Yeah, so it finds this counterexample here. That is an ugly counterexample. It's not minimized. Also, it's got all of these free variables, and I meant for all the terms to be closed here, right? So what if I wanted to write, find me only closed terms? Well, now I need a judgment form to tell it what closed means. Well, this is at least one way to do it. So define judgment form, you write things that look like judgment forms. And this is saying, numbers are closed and lambda's closed as long as if I substitute away all these arguments in the body with 0, just picked arbitrarily, I get a closed term and so on. And with that closed judgment, now I can write this revised property that says, find me a closed term. Make sure that any E you pick is either not closed or it has a unique step. So this way I will get a somewhat nicer example. Actually, I won't. It will not find anything in 10,000 steps or 100,000 steps, because its random generator is too unlikely to generate a closed term. And then if it does happen to generate one, it turns out to be a unique step. So another thing I could do at the end, I want to use, the important part of this slide is Redex check satisfying closed unique step. So this is helping the random search by saying, first make sure you satisfy this judgment form. And then instead of just generating random terms, it works with the judgment forms and finds them. And then this will succeed. But to do this, I had to, it turns out that this satisfying thing doesn't know how to deal with dots in their full generality. So I just made a sublanguage that has subst1 only deals with one argument variables in lambdas, and closed one similarly, and then it can work and it will find I have to extend the grammar with this other part. But again, as we've seen, I can just throw in these extra non-terminals. Since this is the last thing I want to run, let's just try running. Okay. Throwing in some extra non-terminals here. My intent is that E1 and V1 are subsets of E and V, and big enough subsets that I find interesting counterexamples from them. And you can see it found a nicer counterexample for me this way. It's still kind of big. We'd still like to have some minimization tools, but at least I'm not skeptical because there's free variables everywhere. Right. So that's the idea. I should mention that there's a lot of work has gone on to this random test generation to get these different tools and techniques, and these are some, at that time, students who worked with Robbie to build those tools. Xiaohong did such a great example setting us up. He even set up my other example, which is sort of multiple threads. So what would that look like in this world? You would add a pair form and so on. We don't have sort of the nice structuring that K has for making things modular and inferring generalizations for you. There are ways to write extensions. But that's all the idea. If you're interested in more, whenever you get Racket, you're forced to have Redex, if you get the main distribution, so it's already there for you. You can find out more information at the Redex specific site, or there's a whole book if you want to look more at reduction semantics and how they're used inside of Redex. So, happy to take more questions. Thank you.
Okay, at the risk of sounding like a broken record, what's your story for type systems? I saw that the judgment there had quite a general inductive syntax, so can you use that for type systems?
That's what we use to write down type systems.
Okay, in that case, what works and what doesn't? Can you generate like random well-typed terms using your testing infrastructure?
Yeah, absolutely. That's the main use case, really, because you're otherwise generating random terms are unlikely to be typed, right?
Well, that was actually my next question. If you are just generating random terms, how do you make sure they're typed, or do you have some more clever kind of symbolic exploration?
So the satisfying with a type rule written with defined judgment form, that is the more clever thing, right? And that's Burke's work, his dissertation on how to do that search. And I glossed over it, but the reason these different random generations work better in some cases and worse in some cases, so you really need a mixture of these things. But if you have a type system, you definitely want that one. Yeah.
Cool, thank you.
Yeah.
Hi, thanks for the talk. I think the first manual version of substitution you defined was not capture avoiding, was it?
That is correct.
And the second one is that is derived
That's
by...
right. Yeah, the automatic one was, and that is technically, if you happen to notice the weird variable names it picked, that was part of it. I'm not going to find it. But it made up, oh, it's in the other tab. It made up like X17 in weird angle brackets because it needed to do the making up names to make it capture avoiding. So in this case, I wrote down a manual one that I didn't intend to be capture avoiding. I wanted to only consider closed terms, and that's why it was important to me in the end to have the closed judgment form. Great question.
Thank you for a great talk. I have two questions. First is that does Redex support big step semantics or denotational semantics, not other than reduction-based semantics? And second is that does Redex generate proof verifier-friendly output such as ROC or lean?
Let me answer the second question first. This is work on generating proof things. I can't comment on it much. I've only just looked at it a little bit. But for people who know what they're doing, I encourage you to look at Redex Plus or Redex'25 here that will have more answers to that question. The first question about big step semantics, you can write them as meta functions. So we often do that. And then we get a certain amount of type setting. The tools in Redex are less good at it. The meta function either gives you an answer back or it doesn't. Maybe that puts your head in the right space for trying to write the proof. I don't know. But we'd like to have better tools for that, in fact. Yeah. And the judgment forms may be somewhere in between. You could also use that to write big step rules, and the tooling is a little bit better.
Now it's coffee break, so let's keep asking questions during the coffee break. We'll be back at 10:30. Thanks.
Thank you.